Welcome to Unite Now, where we bring unity to you, wherever you are.
Hi, and welcome to this session on mobile performance with the Burst compiler. My name is James Greenhalgh. I work at ARM, where I lead our compiler performance team. I care about how we can make the hardware and software in the ARM ecosystem as fast as possible. I'd like to talk with you today about what my team has been working on alongside developers from Unity to bring even more performance to the applications you're creating with Unity by using the Burst compiler for Android devices. With me is Yury Habets from Unity. Over the last 12 months, more than 3 billion devices worldwide were reached by projects made with the Unity platform. That content was installed 33 billion times in just the last 12 months. That's around 1,100 installs per second. More than 50% of mobile games are powered by Unity, and almost all of the mobile devices on which those games run are ARM-based. That gives us an exceptional platform from which to improve performance and to improve the ability of game developers to express themselves on ARM platforms. Unity and ARM have partnered to improve performance on the billions of mobile devices that make up the Android ecosystem. We're doing this to allow developers to spend more time creating awesome content through improved performance by default and a great developer experience when targeting ARM-based devices. This partnership is important for ARM. Unity developers make up a huge part of the end developers for Android, and games continually push our CPU and GPU technology to their limits and encourage us to design better products. For ARM, those products go everywhere. In September, we announced that more than 150 billion ARM-based processors were now in the world. That number is unimaginably big. ARM is involved in automotive, in laptops, in tablets, in servers, in embedded controllers for industry, in edge compute, in tiny microcontrollers for IoT, and of course in almost every smartphone, where we year after year improve the performance of our products to enable developers to bring richer experiences to their partners. In 2019, ARM announced the Cortex-A77 processor, bringing 20% higher performance in the Spec 2006 integer benchmark over our Cortex-A76 announced a year earlier, which, by the way, was itself a 30% performance improvement over Cortex-A75 announced in 2017. At the same time, ARM announced the Mali G77, offering up to 40% more graphics performance over 2018's Mali G76. These strides in processor and GPU performance continue to push the boundaries of what an ARM-based device is capable of. As we look to the future, we see even more opportunity to ensure that technology from ARM works better together to allow for more secure platforms, which are easier than ever for developers to program, and which enable richer experiences for your users. Through our partnership, ARM and Unity are planning to enhance the power of tools available for Unity and Android to further complement the gains in multicore processor performance from ARM's latest processor designs. We're looking at making a real impact on the experience mobile game developers have when targeting ARM platforms, from improved profiling and graphics engine performance through to better compiler technology, more easily able to target ARM's current and future architecture technologies. As the lead for our compiler performance team at ARM, I see my job as making sure that when you write high-performing games, they're translated and optimized into efficient binaries, which make excellent use of the features of the ARM architecture. My team is responsible for the performance of everything from the biggest server designs through to the tiniest microcontrollers, working with open source compilers such as GCC and LLVM, and ARM's commercial toolchains, ARM Compiler 6 and ARM Compiler for Linux. The best thing for me about working on compiler technology is that chance to improve performance by default across a huge range of projects. I really like that through my work, I can help improve the performance of a wide range of devices in the ARM ecosystem. What we would like to talk about today is how you can make use of compiler technologies in your Unity projects to bring out the best of the ARMv8 architecture and unlock the performance of the devices on which your games will run. I'd like to hand over to Unity now to talk about the Burst compiler and how you can use it to improve the performance of your applications.
Thank you, James. Hi, everyone. My name is Yury Habets. I joined Unity back in 2013, starting an Android team which back then consisted of 3 people and eventually taking the role of tech lead for Android. My main focus was always on CPU performance, So I was happy to start working on Burst for ARM platforms and ARM partnership to make sure our users can benefit from maximum performance on ARM mobile devices. So what is Burst compiler? Burst is a compiler technology that converts a subset of IL.NET bytecode to highly optimized native code using LLVM for Unity apps. Highly optimized native code output means that you're going to get better performance. In some cases, much better performance. This is why Burst plays a very important role in the Unity's performance by default principle. I'm actually going to talk much about performance today. Burst is primarily designed to work with the Unity job system and the new data-oriented tech stack, or DOTS. What is really important, Burst is not a general-purpose compiler. It's a part of Unity and is made to make your Unity games run faster. It supports a wide range of platforms starting from desktop standalone to consoles, and most importantly mobiles, iOS and Android, which is what we're going to focus on in this talk. Now let's move on and see, why is Burst fast? If you think of it for a moment, you'd probably say, why not just use LLVM and let it produce native code? Well, first of all, LLVM doesn't have C# support at the moment, and C# is the language of choice for Unity for a number of reasons. It's capable of solving most problems and delivering top performance at the same time. You may say, okay, but Unity already has a technology that converts C# code into C++ that is later compiled into machine code, and the result is faster than running mono, and I mean IL2CPP. Why do you need one more intermediate step? Well, IL2CPP is a wider concept, while Burst is deeper. IL2CPP has larger C# features support, while Burst does more analysis and optimizations of a smaller fraction of your code. As I mentioned before, Burst is not a general-purpose compiler, so it has the necessary knowledge of Unity APIs that allows for optimizations that a normal compiler won't be able to deliver. For example, Burst knows that native arrays don't overlap in the memory or don't alias, which allows to vectorize your code. James will talk about vectorization in detail later. Burst also knows your hardware, because for optimal results you need to specify the target CPU. And in a typical Unity style, we provide you the possibility to handwrite your assembly code if for some reason you are not satisfied with the output. For that, we expose hardware intrinsics. Now let's take a step back and look into the last two items. Does it remind you of anything? So there was a remarkable talk by Mike Acton called Data-Oriented Design in C++. And he said, know your hardware, know your data to get maximum performance. And Burst does possess this knowledge. So here is another difference between Burst and IL2CPP. Burst is more targeted towards data-oriented design, while IL2CPP has better support for object-oriented techniques. Now on to some details about how Burst actually does its magic. You write your C# game code, then you click Build, and your code is compiled into .NET assembly, which has an extension of DLL. This assembly consists of IL code, or .NET Intermediate Language, and could be run on a mono VM virtual machine. Burst analyzes and manipulates that code and converts it to LLVM Intermediate Representation Language, or LLVM IR. Good thing is that it's relatively easy to map IL to IR, despite them being based on different technologies. And this is where the knowledge of the Unity APIs by Burst kicks in. Then a custom build of LLVM is used to compile and optimize that code, and finally a platform linker is used to generate the output library. In case of Android, it's called lib_burst_generator.so. So this is the compilation pipeline, or what we call AOT compilation, or ahead of time compilation, used when you build a game. In the runtime, the calls to bursted functions will be routed to this native library instead of just running the .NET code from the initial assembly. Burst also works in the Unity editor when you enter the play mode. We call this just-in-time compilation. It uses a similar pipeline with some features that are specific to the editor. So, what do you need to start using Burst in your project? You write your code in C# around job system and entity component system, like this super simple job I've written here. And then a single line of code is needed. This is it. You just need to add the burst compile attribute and you're done. Please note that if your type and functions are not marked with the burst compile attribute, your code will not be bursted, meaning we don't burst all the code by default yet. This is an easiest use case. In a typical Unity way, we provide a widest range of tools to address the needs of all our users, from novice to the most advanced hardcore professionals who want to turn all the knobs to achieve the maximum performance. So to summarize what you've just seen, Burst is free performance. Like, really. Okay, of course it has some limitations. So first of all, it works only with a subset of C# language we call HPC# or high performance C#. To get rid of garbage collection, it doesn't support reference types, namely classes. Second, it takes time to compile because the more you optimize, the slower your compile times. This is a serious issue that our team is working hard to solve by introducing different layers of caching and other techniques. Third, it requires a native linker. In our case, it's Android NDK. But since you already need it to build with Unity and IL2CPP scripting backend, it's not really a big deal. And finally, debugging is an issue because we are basically replacing a call to a managed function by a call into native bursted functions. Good news is that Burst 1.3 preview has debugging support, so make sure you are using the latest Burst package version if possible. Done with the theory, now let's jump onto a device and see the performance gains in practice. So we've built a demo with 3 playgrounds using Unity Physics, which is a stateless, lightweight engine written in C# and targeting dots, with source code available. We selected Unity Physics as a core demo component because it is math-heavy and naturally benefits greatly from burst and vectorized code. The camera and the interactions are scripted and no one touches the screen. We built the project for Android, 2 versions, one with burst enabled, another without burst. You can see it on the video side by side. I've made this video for easier comparison of 2 cases. It is built using Unity 2019.3, latest version of the burst package, scripting backend is IL2CPP, it is targeting 64-bit ARM, and is running on a Samsung Galaxy S10 phone, EU version with Exynos and Mali. The phone is in a thermal condition that is very close in both parts of the demo in a cool-down state, no throttling after some 5 minutes of rest. So you can see that the difference in frame time is at least 2x, with burst being faster obviously. And please make note that quite some rendering is happening here which is not CPU heavy. In a thermally throttled state, the difference stays about the same, but I must say that it makes much longer for the bursted demo to make a device to start to throttle. As you can see, in some scenes the difference comes up to 4x. That's outstanding results, which allow you to handle more content in your games or to lower down the power consumption with the same content, meaning longer battery life, less overheating during long game sessions, and greener planet. Now back to James.
Thanks, Yury. So that's the Burst compiler, available today in the Unity editor when targeting Android devices, and capable of greatly improving the performance of your projects. Burst is a great technology for exploiting hidden parallelism in your applications, and is particularly helpful for games and applications making use of physics and machine learning algorithms. My work at ARM tends to be around improving a set of benchmarks, where your only indication of success is a number getting a little bit bigger. Working on this collaboration with the team at Unity, I've been able to see compiler performance in a new light. When we first got access to builds of the demo that Yury's just shown, I was amazed. I took the phone that we had the demo running on around everyone who was left in the office at 6:30 on a Friday night to show them this really powerful visual representation of what the compiler technology they were working on for the ARM architecture could do. A really great thing about Burst is that it allows you to make use of the powerful Neon technology that's already available on ARM-based devices. I'd like to give you some insight into that technology and where it really shines. Neon is a packed SIMD, single instruction, multiple data, vector architecture, first introduced with ARM v7a and enhanced in ARM v8a, which allows you to perform computations across multiple data elements in parallel. A Neon register holds multiple elements of the same data type in lanes, and the Neon instructions perform the same operation across those lanes. For example, in this slide, we're showing the behavior of a Neon fadd instruction from ARM v8a, operating on 32-bit floating point values. Each lane in the first vector, x1, x2, x3, and x4, is added in parallel to the second vector, Y1, Y2, Y3, and Y4, and stored in the destination register. That is, rather than computing one floating point addition in an instruction, Neon allows us to compute 4 floating point additions in a single instruction. These vector instructions are executed efficiently by the processor implementation, allowing for speedups of multiple times over scalar equivalents. The Neon instruction set provides hundreds of operations, which are useful in computing fields like physics simulation, image, video, and digital signals processing, compression, artificial intelligence, and more. Wherever you need to perform the same calculation in parallel across a large dataset, Neon can be a good fit. Our goal in the compiler is to make Neon as accessible as possible to developers, and in turn to allow as much user code as possible to make good use of the Neon instruction set. In my team at ARM, we spend a lot of time thinking about how we can make Neon more accessible to developers. By far, the most convenient way to do this is for the compiler to just make good use of Neon on your behalf. The technology that allows this is called auto-vectorization. An auto-vectorizing compiler looks at the memory access patterns and the operations of a program and looks for opportunities to use vector instruction sets. In the example code on this slide, we have a loop using floating point data types and adding 2 arrays together. An optimizing compiler can take this code and turn it into something which makes use of the Neon add instruction we introduced on the previous slide. On a large, powerful, out-of-order processor like Cortex-A77, this can allow for up to 8 parallel additions every single cycle. Across a vectorizable algorithm, this can quickly add up to huge performance improvements. The Burst compiler is able to take advantage of auto-vectorization technology to automatically introduce Neon instructions where the compiler thinks it will result in a speedup. While auto-vectorization is great, you get it for free from your compiler, it doesn't make for the easiest programming model, and the compiler is not always able to figure out the best instructions to use. We're working to improve that, and one of the outcomes of the collaboration between ARM and Unity will be improved auto-vectorization in the Burst compiler. But sometimes you need to take more direct control over your program performance. For users who know they need access to efficient vector instructions, the Unity vector classes in Unity Core give a high-level interface to vectors of 2, 3, and 4 elements of integers or floating point data types, along with a large number of high-level mathematical functions on those vectors. Keeping with our example from the last slide, this slide shows the implementation of a vector addition over 4 floating point values. Burst is able to take this code and compile it to the same Neon instruction as we saw in the previous examples. So these are 2 vector programming models available to use. You may ask, which is the most appropriate for your project? The great thing about auto-vectorization is that where the compiler is able to apply it, it comes for free. As compilers get better over time, more and more patterns are able to be recognized by the optimization passes, and so code continues to improve. At the same time, that puts you at the mercy of the compiler. If the compiler doesn't know your patterns, it might miss an opportunity to use vector instructions. In particular, this can happen when the layout for data which the compiler expects differs from your data layout. Auto-vectorizing compilers like to work across arrays of data. For example, for a vector addition, they're happiest if you're adding together 2 arrays of x coordinates, or 2 arrays of y coordinates, 2 arrays of z coordinates. But more often in games programming, when you want to express an operation over vectors, you would have these coordinates in arrays. In this layout, the x, y, and z coordinates are scattered across memory. An auto-vectorization compiler, looking at this layout, might see a problem to solve and use gathering instructions to get back to a vector of x, a vector of y, and a vector of z. This can create inefficiencies, or in the case of larger data structures, can prevent auto-vectorization entirely. When taking explicit control of vector code generation by using a programming model like Unity's vector math routines, you're able to ensure that maths happens the way that you'd expect, retaining the logical benefits of keeping an array of structures layout while ensuring efficient code generation. If you're able to make use of this explicit model of vector programming, you gain predictability over the Neon code generated and improved portability between platforms. Of course, the downside is that you need to make a manual intervention. You need to rewrite your code. So that was an introduction to the power of Neon technology, available in all ARMv8A Android devices, and providing packed SIMD technology, which allows us to exploit the data level parallelism in your physics and machine learning workloads. Projects made with Unity can use both automatic and explicit vectorization techniques to target Neon and unlock additional performance when working with the Burst compiler. I'd now like to hand back over to Yury, who will show you how to use Burst to get great performance from your Unity project.
Okay, now let's get to the Unity editor and see how you can use Burst in your projects. I'm opening here the demo project I've shown earlier in this video. So first of all, Burst is distributed as a package. It gives you quite some flexibility because it's easier to add, remove, or update it independently of the Unity version. So let's go to the Package Manager menu. And here you can add a Burst package to your project. As you can see, it's already present in this project. It may also be present because it was pulled as a dependency of another package. For example, Entities package depends on Burst. So whenever you want to use entities, you'll get the Burst package automatically. Please pay attention that there are final and preview versions of Burst. Since it is in active development right now, it may make sense for you to try a preview version because it may add shiny new features that you've been waiting for. We're happy to hear your feedback about Burst in the Unity forums. Here's also a view documentation link which leads to Burst documentation. It's a great piece of information with both basic and very advanced topics which we maintain at the most actual state. For example, you can read more about memory aliasing and loop vectorization and the intrinsic APIs to control them. Now let's switch back to the Visual Studio. For a basic Burst usage, as I said before, you can just add the Burst compile attribute to your code like it's done here. So this is a user script. Let's switch back to the editor again and open the profiler. Here's a capture I've made from a device with this demo. Here's a frame captured. And as you can see, this is the physics job which takes most time in the frame. As you can see, it has a Burst attribute here in the profiler. And if we switch back to the code, here it is. We've added the Burst compile attribute for you. This is a part of the physics package. For more advanced usage and deeper performance analysis, you can use the Burst inspector window. Let's get back to Unity editor, jobs, Burst, open inspector. And here it is. On the left, you can see a list of all the jobs in your project. The ones that are not grayed out are bursted jobs. Let's select one of the jobs, for example, this one. On the right, you can see several tabs which represent the stages of the Burst compilation pipeline I've talked about earlier. You can go through the .NET IL code or the LLVM but the ultimate output is the assembly code, which you can see here. Let's switch the target to ARMv8. As you can see, the assembly immediately switches to our target CPU. Along with the assembly code here, you can also see the reference to the lines of the C# code, so it's easier to match. If we scroll down a little bit, so here we can see the calculation of the vector cross product, which is vectorized and uses Neon instructions. You can inspect it, and if you think that you can write assembly code better than this output, then we're working on a feature for you. Neon intrinsics are on our roadmap, and they will allow you to handwrite your assembly code in C#, squeezing maximum performance out of your game. So that was a very basic practical intro into Burst for ARM.
Thanks again, Yury. So that's how to use Burst from your Unity project to make use of the ARMv8A instruction set and accelerate the performance of code running on your users' ARM-based devices, using compiler optimization features such as auto-vectorization targeting ARM Neon technology. Before we finish today, I wanted to give you some insight into the future direction of travel for the ARM architecture. In 2016, ARM announced an exciting new vector instruction set, the Scalable Vector Extension, known as SVE. SVE was then further augmented in 2019 with fixed point and DSP instructions to become SVE2. SVE2 expands on Neon by introducing the concept of scalable vectors. Neon has two possible vector sizes, 64-bit registers and 128-bit vectors. SVE2 does away with the idea of a vector size, with an assembly language that allows for users to write against multiple vector lengths simultaneously. As ARM and its partners develop new processors, They have the choice of which vector length to implement, from 128-bit up to 2048-bit. This is the scalable in scalable vector extensions. In the Neon examples earlier, we saw that a Neon add operated on 4 32-bit elements in a packed 128-bit vector. In SVE, the number of 32-bit elements varies with the vector length. For example, with a 256-bit vector length, we would have 8 elements in a vector register, and for a 512-bit vector length, we would have 16 elements in each vector register, meaning we might be able to compute 16 additions in parallel. The concept of SVE is that programmers can write their vector code against a single target instruction set and have the performance of that instruction set scale transparently as different decisions are made on the appropriate vector width for different processors. Programmers looking to take great advantage of the scalable nature of SVE need to see the world in terms of vector instructions, which may load and store different amounts of data depending on the eventual vector length of the real hardware. For this reason, SVE has been designed to allow a compiler as much scope as possible to use auto-vectorization techniques. The instruction set provides predicated operations, easier access for conditional operations, and new first faulting loads to expand the range of loops, which can use vector accelerations. When SVE2 is available in devices, we intend for compiler support to also be available, both through an explicit model expanding on the Neon intrinsics available in C and C++ compilers today, and through auto-vectorization from compilers which implement the SVE2 target. ARM invests substantially in compiler technology across all of our ecosystems. We provide improvements to open source toolchains like GCC and LLVM, and we provide improvements to our ARM Compiler 6 and ARM Compiler for Linux products. We do that to ensure that the latest versions of the ARM architecture have fully featured code generation support, unlocking the latest performance and security features of ARM's processor technology. We make these investments into the foundational compiler technologies on which programs are going to run in order to ensure that the developer experience on ARM is as good as it can be. Our compiler development complements our strategy of ensuring that developers for Android have access to great tools for performance analysis through ARM Mobile Studio. Our ARM Mobile Studio is a suite of free-to-use tools which help game and app developers to reach more of the mobile market by efficiently optimizing and debugging high-end content. It includes ARM Performance Advisor with effective profiling advice, Mali offline compiler for compiling shaders and kernels from OpenGLES, OpenCL, and Vulkan, ARM Graphics Analyzer for tracing graphics performance issues easily, an ARM Streamline Performance Analyzer for a view of performance across both the CPU and GPU. The Studio can be used with projects made with Unity. To learn more about ARM Mobile Studio, you can visit the ARM Mobile Studio page on developer.arm.com. ARM has a vision of our products working better together in a whole system solution, which brings out the best performance of the applications your users care about. For our collaboration, ARM and Unity are working to showcase the potential of your Unity projects through better tools and compilers, giving a great developer experience when targeting ARM devices. Today, we've given you an introduction and tutorial to using Burst on ARM devices to improve the performance of your applications and games. I'm really excited to know that this compiler technology will help to bring out the power of the Neon instruction set implemented by all 64-bit ARM devices in the Android ecosystem, and that it's available in the Unity editor today, ready for developers to build richer experiences for their users. Thank you for attending our session. We hope that we've inspired you to try the Burst compiler and to start using it in your project to unlock even better performance on ARM-based Android platforms.